Hi, good evening, everyone. Hope you're doing all right. We are going to go through chapter 13 today, which is on solutions. So, okay, so a solution, remember, is a homogeneous mixture of at least two things. You'll have a solute and a solvent. The first set of slides here is talking about a solution, and not all solutions are like liquids and liquids or solids and liquids. Sometimes you can have gases dissolved in liquids. So this first thing is a picture of a lake in Africa that's sat above a bunch of tectonic activity, and there was a bunch of dissolved gases in the lake. And because the lake was particularly deep, the gas was able to stay in solution. But at some point, the or the lake depressurized and the gas escaped from the water. And because CO2 is more dense than the rest of the atmosphere, it drifted down the side of this mountaintop and killed a bunch of people and killed a bunch of their livestock because they suffocated. So now they degas the lake on a regular basis. There's a picture of this guy like trying to release some of the trapped gas that happens in this lake. So the carbon dioxide and water mixture that we saw at Lake Nyos is an example of a solution where we have two substances that are evenly mixed throughout. Solutions are common. Most of the liquids, gases that we encounter are actually solutions. So, the oceans are not pure water. They are a mixture of salt and water. Blood plasma is also an example of a solution. There are liquids with several solids dissolved in there, and there's also dissolved gases in your bloodstream as well, like oxygen and CO2. That's how oxygen gets transported to our muscles and CO2 gets transported away. And it can be composed of, like they said, Lake Nyos here, a gas and a liquid. So there are solutions that we call gaseous solutions, and this is a mixture of two or more gases. The air that we breathe is an example of a gas solution. So there's an evenly mixed proportionality in the atmosphere of nitrogen, oxygen, argon, some trace elements. Liquid solutions, which I feel like is where we spend kind of most of our time. We can have gases dissolved in liquid like soda water. We can have liquids dissolved in liquid like alcohol, vodka. You buy hard alcohol, you don't buy pure alcohol or pure ethanol. It's cut with water, and then that gives it whatever proof it's at. And then we can have solids dissolved in liquid. That's like a salt dissolved in liquid. And you can actually also have solid solutions. So things like brass or steel or other metal alloys will have two different materials, not bonded, but mixed together in solid form. And then you get kind of the perks of both metals or multiple metals. So within a solution, you're going to have a minimum of two components. The majority component is known as the solvent. That's the thing that's kind of like doing the dissolving. And then the minority component is called the solute. So if we have a solid liquid solution, which a lot of times we come across these solid liquid solutions, the liquid is usually referred to as the solvent. It's what's ever doing the dissolving. And then because of the planet we live on and water being so prevalent, we have a whole area of chemistry dedicated just to aqueous solutions, aqueous chemistry. So we will give all solutions where you have something dissolved in water will be classified as an aqueous solution. We have other solvents used in labs. If, for instance, we wanted to dissolve something like oil, we wouldn't use water. It's not going to dissolve. We would have to use a different type of solvent, specifically a nonpolar solvent. So this slide is just sort of indicating that likes dissolve likes. So polar things get dissolved by polar materials. So water will dissolve other molecules that look asymmetrical or polar. nonpolar solvents are things that have a relatively balanced structure. Usually they're hydrocarbons. So the formation of a solution with water in a solid, how does that happen? We can use our example of NaCl, so table salt. And when it's in solid form, the Na and the Cl are fused together in a lattice framework structure. There is a certain tug or pull between the sodiums and the chlorines, right? That ionic bond. When this thing gets dropped in water, water is a polar molecule. So the oxygen side will have an overall negative charge and the hydrogen sides will have an overall positive charge. And what that does is there's an attraction between the negative side of our water molecule and that positive sodium ion. And vice versa, the positive hydrogen side of the water molecule is attracted to the negative chlorine ion. And so if this attraction between the water molecule or the solvent and our solute, what's going to be dissolved, if that attraction is stronger than the attraction between the solute and the solute, or even the solvent, then this thing will break apart. So the sodium and the chlorine, that bond just isn't strong enough to outweigh the pull of the water molecule. And so on the next slide, we can see here that we've got the water molecules almost picking off the chlorines and sodiums. And at some point, the water molecule or the volume of water will contain the maximum amount of salt that it can possibly contain. And you may get some of the salt precipitating on the bottom. Now, the chlorine is sort of buffered by the positive charge of the hydrogens, and the sodium's sort of buffered by the negative charges of the oxygens or get surrounded. So these two things don't really interact because there's such a high quantity of water. If I was to evaporate the water, like heat this up and these water molecules started to vaporize, move into the air, there's more room now for the sodium and the chlorine to bump back into each other. At some point, you evaporate enough water, you're going to precipitate the salt back out because it recombines. So in a solution of NaCl, we're going to get Na plus and Cl minus ions dispersed in the water. And it's important that we notice that when we take this salt, we get its ion form. So it's not just Na and Cl, it's Na with a plus charge and Cl with a minus charge, meaning we have these charged ions. That makes this thing an electrolyte solution. So when we take our salts and dissolve them in water, and when I say salt, I mean loosely anything that's like a metal combined with a non-metal or a polyatomic ion, we're going to get an electrolyte solution. So the thing with solutions is that you've got to be able to describe a solution's concentration. It's not enough just to say, oh, I have salt water. You have to like let the reader know how salty is that water. Is it the saltiest water they've ever tasted, or is it just like a little teeny tiny amount of salt that can't be detected? So every material, every solvent is going to have a certain solubility to whatever the solute is. So an example of our solubility for sodium chloride, and this is temperature dependent. Usually they standardize it to 25 degrees Celsius. If I change this temperature, these two numbers will adjust. But the solubility of sodium chloride is roughly 36 grams of salt can dissolve in 100 grams of water. If we've reached that point where we have 36 grams of NaCl and 100 grams of water, we would say that the solution is saturated. So a saturated solution is a solution that holds the maximum amount of solute within whatever the given condition is, 25 degrees Celsius. An unsaturated solution is really going to be anything less than that maximum amount. So 24 grams of NaCl in 100 grams of water. That would be an example of an unsaturated solution. 0.25 grams of NaCl in 100 grams of water would be another example of an unsaturated solution. So there's one saturation point, there's one saturation solution, and that holds the maximum amount. There's multiple unsaturated solutions. Let's say I had something like 8 grams of NaCl in 50 grams of water. If this is the solubility here, this is in reference to 50 grams of water. So what you can do is just multiply both these numbers by 2 to get it to 100 grams, right? So this would say that we have, it's equivalent to what, 16 grams of NaCl in 100 grams of water. Is that saturated? No, it's an unsaturated solution. There is, in rare occasions, these things called supersaturated solutions. And a supersaturated solution is a solution that actually holds more than the normal amount at that given temperature. So let's say we had a solution where it was like 38 grams of NaCl in 100 grams of water. That would be over our saturation point. We would call it supersaturated. How does that happen? You can make that happen if you heat the water up and pack, because warm water holds more salt than cold water. So if you heat the water up and you pack some more salt into it and then very, very slowly cool it down, sometimes it'll retain the salt, but it's a very unstable situation. So if you have like, you know, an eyelash that drops in there or a speck of salt that drops in there, it'll precipitate out any of the excess salt and get you back to your saturation point. Okay. So as far as what's soluble and what, we talked about this a while back, but we have those solubility rules. There's certain instances where the attraction between, let's say, calcium and carbonate, the attraction between those ions is greater than the attraction of either of those two things to the water molecules. So it won't break apart. So you don't have a solubility for this thing. The solubility is, you know, ideally it's 0. And that's why you get a precipitate. There are things that are not salts, so they're not metal non-metal combinations, they're molecular, and they can dissolve in water. One example is table sugar. Table sugar has this formula here, C12H22O11, and it is molecular. Molecular meaning it's all non-metals. There's no metal non-metal charge thing here, it's just a molecule. This is polar, so it will dissolve in a polar molecule, but this thing doesn't break apart into ions. It just breaks apart into its simplest molecule. So each adjacent molecule breaks apart, but the molecules themselves stay as packets. Non-polar solids like lard and vegetable shortening will not dissolve. So back to that concept of electrolyte and non-electrolyte solutions. On the left here, I have table salt dissolved in water, and on the right I have sugar dissolved in water. Now, how do these two things different? Well, table salt NaCl is a metal and a non-metal, so it's going to produce ions in solution. That's what gives it that current or that the electrolyte qualities that I can pass a current through here. On the other hand, my sugar molecules or my table sugar breaks apart just into the individual molecular packets, but the packets stay as a whole. These atoms don't separate from their partners to produce any sort of charged ion. So we can't pass a current through here. So this would be classified as a non-electrolyte solution. So when you drink Gatorade, it's the dissolved salts in it that are giving you the electrolyte properties, not the sugar. The sugar is there just to make it digestible. So why do we give a temperature stamp to our solubility? Like we said, okay, for instance, salt is, at 25 degrees Celsius, 36 grams of salt can dissolve in 100 grams of water. Well, the reason we have to give it a temperature stamp is because these solubilities will actually change based off of the temperature. If you have a solid, and it's important to note that it's a solid, if you take a solid and you dissolve it in water, when you increase the temperature, so on this graph, we're increasing the temperature on the x-axis, so we're getting warmer as we move this way. The solubility is on the y-axis. You can see that our solubility increases for all these different salts as we increase the temperature. So the warmer the water is, the more salt you can dissolve in it. So water at the equator tends to be saltier than water in the higher latitudes because it's warmer, it can dissolve and carry more of the salt. let's see here. Recrystallization. I don't really test you guys on this, but just FYI, if you ever want to like purify a material, one way you can do that is to dissolve it in water and then evaporate the water and let it recrystallize. So let's say you had a sample of, NaCl, but it had impurities in it. You could dissolve that salt in water and then evaporate the water, and the impurities will sort of be pushed out of the new crystalline structure. Recrystallization is a way that they make rock candy. So if you ever bought this or bought this for your kids and it's like super overpriced, all it is table sugar. That's all. I mean, you could make it in your house if you wanted to. They've just taken table sugar and recrystallized it over a string. So we can also have solutions where we have gases dissolved in water. These have sort of different properties than when we have a solid dissolved in water. Lake Nyos was an example of that. Also pop, or soda pop. I guess in the South they call it soda. I'm used to calling it pop up north, but whatever. It's carbon dioxide dissolved in some sort of liquid, usually, right? Water, sugar, some other chemicals in there. And, even ocean water has dissolved gases in it. Even our tap water to some extent has some dissolved gases in it. That's why fish can survive in the water. So a lot of times people think, well, fish don't, they don't breathe. They do breathe. They just do it in a different function. They don't have lungs like we have, where we extract the oxygen from the air. They actually extract the oxygen directly out of the ocean water. So let's see. Okay, so how does dissolved gas, how is dissolved gas affected by temperature? So it's actually the opposite. So when you have dissolved gas, gases in water decrease in solubility with an increase in temperature. So the warmer the water is, or the pop or whatever it is, the less gases it can hold. So when you think about serving pop, we don't usually serve it warm. We usually serve pop and beer and effervescent drinks cold. One of those reasons is because it preserves the fizz. So it doesn't flatten out. If you pour a bunch of warm pop into a cup, you get like a really big sort of foamy head, and then like all the fizz is gone and it's not fun anymore. So that is based off of the temperature. Similar thing happens with like, they talk about climate shift and, global climate change and warming ocean temperatures. The warmer that, a body of water is, the less oxygen it can hold. And so one effect that we're seeing with climate change is that fish are dying because they're not able to extract the same amount of oxygen out of the same body of water because it's too warm to hold it. Another thing that we want to layer on top is this thing called Henry's Law. So this doesn't apply to solids. You have solid dissolved in water. It doesn't matter if you're at sea level or on the side of a mountain, it's going to do the same thing. But when you have gases dissolved in a liquid, the higher pressure that sits above the gas, or rather above the liquid, the more gas can be dissolved in that liquid. So if I have, let's say on the right here, I have 2 ATMs, and on the left, I have 1 ATM, 1 atmosphere. This can hold more gas because it has twice the atmosphere sitting above it. This just allows the gas to sit in liquid better. You can think of a closed can of pop. So this is under pressure, under CO2 pressure. When you open the can, you release that pressure, and that's when you start to see the pop fizz. If it's, like a clear can of Coke or something, you don't see the fizz when the bottle's closed, but when you open the bottle, that's when you start to see all of the bubbles come out of solution. The reason they're coming out of solution is because you decrease that pressure head sitting above, and now the gases can come out. Okay, so all of these solutions, we've got to explain what the concentration is. It's not just enough to say, I have hydrochloric acid. You've got to tell the reader what that percentage is of hydrochloric acid to water. Is it something that they have to be really careful about, not getting it on their clothes or skin? Or is it something that is so small in concentration that it doesn't really have any sort of effect? So the three ways that we're going to describe these, I'm going to just kind of summarize all these slides on our whiteboard. And there are more ways to describe concentration than these three, but these are the ones that I will test you on and you guys will see with your lab. So the first one is something called mass percent or mass percent. Sometimes it's written as M over M percent. And the equation for this is the mass of the solute over the mass of the solution. And then we're going to multiply that whole thing by 100, okay, because we're in a percent. One thing that's important to note is that the denominator for this is talking about the entire solution. So sometimes people will get a little ahead of themselves and just take the mass of the solute divided by the mass of the solvent. But you actually need to include the solvent and the solute together. So make sure you have mass of solute plus the mass of the solvent as your denominator. And we'll do some calculations with these in a little bit, but let's get the three types of concentrations. The next one is kind of a funky one. It's called mass volume percent. Mass volume percent, which is a weird way to talk about percentage because usually they need to have the same units, but I'm just going to go with it. So MV percent. This is going to be the mass of your solute divided by the mass, sorry, let's ditch that, divided by the volume of your solution. And the units on this one is really needs to be defined. The top value is in grams. The bottom value is in milliliters. Okay, and then you multiply this whole thing by 100. That's just the way it goes. It's just going to be in milliliters. So this would be, you know, if I said, hey, I dissolved 14 grams of salt in 55 milliliters, you'd be able to come up with a mass volume percent for it. The last way that we are going to express concentration, which is probably the most common way, is this thing called molarity. M-O-L-A-R-I-T-Y, molarity. The unit for this is a capital M, big M. Okay, it's not the little m, that's a meter. It's not MOL, that's mole. Molarity is going to equal your moles of the solute, that's the thing that's getting dissolved, over liters of solution. So just note that mass volume percent is in milliliters. Molarity is in liters. We want to be using the correct units. This one is, I feel like this is used the most often in real life settings. Like if you guys were actually in lab, if we were in there together, you'd be seeing containers pretty regularly that say, hey, 6 molar HCl, 1 molar NaOH solution, this, that. So when looking at all of these, they're really just sort of like, they're equations with 3 variables, right? I have the percentage, I have the mass of the solute, and the mass of the solution, right? So 1, 2, 3, here, 1, 2, 3, and here, 1, 2, 3. The only thing that's different about the molarity one is it's not a percentage, so we don't multiply the value by 100 at the end, okay? These two get that multiplier, this doesn't. So let's say, let's do a problem. Oops. What is the mass mass percent of 33.4 grams of KCl dissolved in 91.3 grams of H2O. So just have you guys work on that one. We'll work with that first equation. Okay, so if it's asking for mass percent, then use the mass percent equation. We're going to use this top one here. Now, my numerator is going to need to be the mass of the solute. So the solute is the solid or what's being dissolved. So that's the KCl. We have 33.5 grams of the KCl. Now, on the bottom, I don't want to put in 91.3 grams solo because that is just the amount of water. We have to talk about the whole solution, and part of that mass of that solution is going to be the KCl. So we actually need to take the 33.5 grams and add it to the 91.3 grams. That I see kind of as a silly little mistake that happens quite often. So just make sure, do you need just the solvent or do you need the solute as a whole? All right, so the total here is going to be 124.8. We'll round at the end. So 33.5 divided by the 124.8. Multiply it by 100 to get it into a percentage, 3 sig figs, so 26.8 by mass percent. You guys may have heard of like this thing is sometimes called parts per 100 because it's per 100%. If you've heard parts per million or parts per billion, those are smaller, even smaller kind of percentage. They're not percentages, but they're smaller values for concentrations of things that are really teeny tiny, but can still have an effect. If it's like a pollutant or something in a waterway. So let's do another one. I'm gonna switch it up just a little bit. Okay, and okay, so this problem says how many grams of KNO3 are in a 1.6 liter of a 4.65%, and that's specifically a mass volume percent solution. I want you to play around with that problem using equation 2. I'll give you guys 2-3 minutes for that. Okay, so for number two, or for this second problem, we're going to look at equation number two, which is our mass volume percent. Why? Because the problem is asking us or telling us something about mass volume. So makes sense to use that one. You're not always given the two things on the right and you solve for the percentage or the molarity. Sometimes you're given the percentage and one of these things and you have to solve for the other. And that's what's going on in this. So we know the mass volume percent. So I know what the whole thing needs to equal. It needs to equal 4.65%. I'm trying to find the mass of the solute. Remember, grams of KNO3, it's whatever the salt is. So we're trying to find grams of KNO3. Do I know my denominator? Almost. I mean, I know my volume. This is specific to milliliters though. So make sure you convert to milliliters. So we're at 1.6 liters, which is equivalent to 1,600 milliliters. Okay, so just make sure to convert. And then don't forget to wrap it up by multiplying this whole thing by 100. All right, so we want to isolate for our numerator here. So we can, divide by 100, divide by 100, and multiply by 1,600. Multiply by 1,600. Or if you plug that into your calculator and then took whatever the fraction was of it and moved to the other side, that's fine too. I just had it 4.65 divided by 100 multiplied by 60. 74.4. 74. Only one sig or two sig figs here, so I guess we have to round to just 74. So 74 grams of the KNO3. So know with concentrations that, a lot of times you're solving for the concentration, but sometimes they give you the concentration and you have to solve for one of the other things. I do want to play around with molarity a little bit, just because that one is used so often. So let's say, we'll do a quick one and then one that requires a little more work. So what is the molarity of 8.7 moles KCl in, 5.46 liters of solution? Okay, so pretty basic here. It's asking for molarity. So molarity equals moles over liters. Hey, look at that. How nice. It's in moles for us. So we can right away plug that in, 8.7 moles for every 5.46 liters of solution. We divide those two numbers out and we get a value of 1.2 sig figs again. So 1.6. And there's two ways that you can write this. So one is to put the molarity unit, which is capital N. Okay, 1.6 big M. But a lot of times we'll use this especially in solution stoichiometry as a conversion factor. So we actually want to preserve the mole per liter unit. So another way you can write this is 1.6 moles of whatever the solvent is, KCl, per every 1 liter of the solution. Okay, so these two are saying the same thing. You can write it as 1.6 molarity or 1.6 mole per liter. But do note molarity is not the same thing as just mole. It's mole in a given volume. So yeah, just be able to kind of crisscross between those two. So if I said, you know, I have a solution and it's 6.5 molar HCl, that's the same thing as saying I have 6.5 moles of the HCl in every 1 liter of solution. Okay, the numerical value goes in the numerator. The denominator will always be per 1 liter. So let's try a problem that asks you to do a little bit more. Because that was kind of a softball, huh? Let's say, how many grams of aluminum hydroxide are in 455 milliliters of a 8.5 molar solution? This is going to ask you to do a little nomenclature as well, because why not? Because it never goes away. All right, so I'll give you guys about 3-4 minutes to try and figure out what you need to do with that. Okay, so for this guy, we want to use number 3, which is telling us molarity, or has to do with molarity. So we know molarity equals moles over liters. Nowhere in this is there the word gram, but hopefully now you guys kind of know that mole and gram are interchangeable as long as you have the formula, right? Because you can use the molar mass to convert between the two. So aluminum hydroxide, you have to be able to write that. Aluminum, Al with a 3+, hydroxide, OH with a minus, flip flop, we get Al, OH, 3. Okay, that's the formula. So I know my molarity. I know my big M. Big M is equal to 8.5, that big M. I know my volume. It's not in liters, it's in milliliters. So I want to convert this into liters, 0.455 liters. Always being really anal retentive about, am I dealing with the milliliter one or the liter one? So 0.455 liters. And we are going to get moles, which isn't what we want, but it's closer to what we want than what we started with. So let's first solve for moles. So I take that 8.5 and I'm going to multiply it by 0.455. And I get a value of my mole value will be 3.8. I'm just going to keep everything 8.675 so that I don't have a rounding error. And this is moles of AlOH3. So what we have to do now, since the problem said, no, I don't want moles, I want grams, is we just have to go ahead and convert this into grams. So 1 mole of AlOH3 weighs, I have no idea. So let's ask Google. Looks like 78 grams. 78 grams of the AlOH3. That will allow moles to cancel and we'll be left just with units of grams. So we take our mole value, multiply it by 78, and we get 300. Okay, so what do I want to round to? 2 sig figs again. I don't know why I keep giving you 2 sig figs on that one. So 300 would just be exactly 300 grams, specifically of the AlOH3. So the equations are not complicated. They're 3 variable equations. The way that we will kind of test is give you things that aren't directly values you can plug in. So being given something in grams or being given something in milliliters or wanting something in milliliters and having to just do little kind of changes here and there. Okay. So how are you guys feeling about these 3 concentration values? All right. Yeah, it's not too bad. I feel like it's not too bad. So let's go into the other 2 topics. First one is solution dilution, which is actually quite easy. And then the second one is solution stoichiometry with, I mean, anytime you hear the word stoichiometry, you know, it's going to be kind of a pain in the butt. So we'll do the easy one first. Okay, we've already kind of worked through all this stuff, so we're good there. Oh, this is one thing I want to talk about. This kind of applies more to when we get into acids and bases, but when you have a molecular compound, like let's say we have glucose, molecular being all nonmetals, whatever the concentration is of the material is also going to be how many moles of that thing you have per liter, right? It's different though when you have a salt, if you have multiple ions. So if I have CaCl2, and let's say that the concentration is actually 1 molar CaCl2. Well, in every given solution, It will contain 1 mole of the calcium because I get 1 calcium for every 1 molecule, but it's going to actually contain 2 moles of the chlorine. Why are there 2 moles of chlorine? Because you get 2 chlorine ions for every 1 molecule that breaks apart. So you kind of get more bang for your buck. So you'll want to take the subscripts and multiply them by whatever the molar value is. If we go to the next slide, we can see an example of this here. Let's say I have sodium phosphate, Na3PO4, and it's in solution. I want to know what the concentrations are of sodium and of phosphate ions if I have an overall solution that's 1.5 molar. Well, looking at this, I want to take whatever my overall concentration is and multiply it by the subscript for that ion. So sodium, how many sodiums are we going to get? We're going to actually get 3 sodiums every time we dissolve one of those things. For the phosphate ion, we only get 1. Okay, I know there's a 4 there, but the 4 is included within the packet. So we actually only get 1 phosphate. So the phosphate concentration should be the same as the overall concentration. The sodium concentration, though, we're going to have to go 1 step further and multiply it by 3. So they have here molarity of Na plus is the subscript 3 times whatever the overall concentration is. So the concentration of the sodium ion will actually be 4.5 molar. The concentration for the phosphate will be the same because it's a 1-to-1 ratio. That doesn't come up a whole bunch in this chapter, but when we get into acids and bases, it's important when we're talking about like concentrations of the acids, if it has 2 hydrogens or 1 hydrogen. We'll get into it a little bit later. Okay, so solution dilution. Solutions are often stored in really concentrated forms in a stock room. So if you guys were in our lab setting, you know, in the back stock room, I don't order like every solution concentration. That's insane. It would take up so much space. Instead, we order 1 really concentrated solution, like maybe we'll order 20 molar hydrochloric acid solution. And then if we're going to run a lab and I only need something with like 2 molar or 3 molar, I'm going to take that concentrated solution and I'm going to dilute it. Just like when you get, you know, concentrated orange juice in that frozen can, and then you dilute it with 3 cans of water. You're cutting the concentration down by increasing the volume. And so there's a really nifty relationship between that, which you could even use for your orange juice if you wanted to. And that's M1V1 equals M2V2. The ones are the molarity and volume of your initial concentrated solution. So that would be like your stock solution. And then your M2 and your V2 are your concentration and volume of your diluted solution. So the ones are the concentrated thing, the 2s are the diluted thing. The ones, because it's concentrated, it's going to be a high concentration with a small volume. All right. The 2s, because it's your diluted solution, it's going to be a lower concentration with a much higher volume. How many variables do we have here? 1, 2, 3, and 4. So you'll be given 3 of the 4 and you solve for the 4th. You may be given the 2 initial things and 1 of the final things. You may be given 2 of the final things and trying to find something about the initial. It's pretty straightforward. I think the trickiest thing people come up with in this is that they like will flip-flop their volumes or something. So let's say, oh, and just so you know, sometimes you'll see this equation written like this, C1V1 equals C2V2, the C standing for concentration. This equation can be used for molarity. It can be used for mass percent. It can be used for mass volume percent. Okay, you can plug any of those in as long as they're the same on both sides. It will work out. So let's do a solution dilution problem. What is the final concentration if I dilute 18 liters of a 6.5 molar HCl solution to 150 liters. Okay. What is the final concentration if I dilute 18 liters of a 6.5 molar HCl solution to 150 liters? So you go ahead and try and work on that. Let me write the equation out for you guys again. M1 V1 equals M2 V2. All right, so let's organize our information. I mean, always too, I always kind of start with how do you know, outside of me specifically telling you to use this equation, that this is what you need to be doing. If you see the word dilute, if you see that there's some sort of initial and final concentration and we're not changing what we are, we're saying hydrochloric acid and we're just happening to dilute it, that's a good indicator. We're going to use this one. So M1, V1, M2, and V2. The one is talking about the more concentrated thing. So in this case, the more concentrated thing is my starting solution, which is 6.5 big M HCl. It says, you know, what is the final concentration? So I'm trying to find M2. My V1 is going to be my smaller volume. So 8.5, not even close, Candace. 18 liters. And our V2 is 150 liters. So just kind of conceptually thinking about how these things relate to each other, this number is going up. You see how that number is getting bigger? Not quite by a factor of 10, but it's going up by a factor of around 8.3. So because this is going up by a factor of 8, this should decrease by a factor of 8 to compensate for it. So we should, as our volume goes up, our concentration should go down. We'll plug it in 6.5. So 6.5 big M, multiply it by my 18 liters. That's going to equal my mystery concentration, which usually you don't do. You don't usually you have a specific concentration you're wanting, and you don't know what the volume is. Okay, 150 liters. So we'll divide each side by the 150 liters, divide this by the 150 liters. That will allow liters to cancel and we'll be left with just a unit of molarity. And we find that we have what, 6.5 times our 18 divided by 150. I get a final concentration of 0.78 big M. Okay, so the concentration did go down quite a bit, but our volume went up quite a bit. So that's not too bad, right? Solution dilution isn't too tricky. What sometimes people will do is they'll use this for solution stoichiometry, which is the next concept that we are going to talk about. So we want to make sure we keep these separate. So this only applies when we have a material and we're just simply adding water and increasing its volume. All right, so let's talk about solution stoichiometry. Oh, FYI, always when diluting acids, always add acid to water. Just so you know, acid to water, safe as an otter. Here is another problem. It says prepare 5 liters of a 1.5 molar KCl solution from a 12 molar stock solution. And it's just like, what is the initial volume? How much of that 12 molar stock solution do I need? So in this case, we're solving for V1. We know the initial concentration is 12. We know that we want a final concentration of 1.5. And for whatever reason, we need exactly 5 liters of it. So we can work this problem to isolate for V1. And we end up getting 0.625 liters. So for the high concentration thing, we need a relatively small volume of it, and then we just dilute it out to 5 liters. Okay, so the last thing that we're going to talk about today is probably the most time-consuming, solution stoichiometry. Stoichiometry, again, being the ability to move from one material to another in a balanced chemical equation, right? When I have a balanced chemical equation, there are coefficients. Those are mole relationships. And so a lot of times when we're working with like an aqueous reactant, it's easier, it's more convenient to give the volume and the concentration than it is to give like grams, because it's already as a liquid and it's dissolved. So what we can do, because molarity, right? Molarity equals moles per liter. Molarity equals moles over liter. If you're given concentration and you're given volume, you can then solve for moles. If you can solve for moles, anytime you can solve for moles and you have a balanced equation, you can solve for another material, whether it's another reactant or product in the balanced equation. Okay, let's go to the whiteboard and we're going to do kind of a flow chart. So the flow chart that we had from chapter 7 was grams of compound A into moles of compound A, into moles of compound B, back into grams of compound B. And to fill in the steps here, right, to go from grams of compound A into moles of compound A. And remember, A is talking about your initial compound, B is talking about your final compound. To go from grams of A into moles of A, we use the molar mass of A. To go from moles of A into moles of B, that's where we use the coefficients from the balanced equation. Coefficients from balanced equation. And then how do we go from moles of B back into grams of B? Well, we have to use the molar mass specifically of B, the final material we're looking for, molar mass. So I'm going to add some limbs to this. So coming out of moles of A, go up and over, and I want you to put volume of A. Because we're not always given grams of a material. Sometimes we're given the volume of the material. And then over here on B, I want you to put a little fork and put volume of B. Sometimes you don't want to solve for grams. You want to solve for the volume. Now, how does volume and mole relate to each other? These two things relate to each other by molarity. Okay, molarity equals mole over liter. If you know your volume in liters and you know your molarity, you can solve for mole. So on this limb here, let's put molarity, specifically molarity of whatever material A is. It has to be directly related to that. And then over here, let's put molarity of B. Now we can add an additional limb down here where we put molarity of A, or we start with the concentration, or we can try and solve for the final concentration. Usually we don't start with the molarity, but we sometimes will end with the molarity of B. T of B. Okay, and this, both of these limbs, we would have to use the volume of A and the volume of B. So these are sort of the inverse of these two limbs up here. We're going to spend some time on this track right here. Okay, and I'm going to kind of ignore the other stuff. So let's go ahead and erase everything we don't need, or I'm going to just rewrite it, what we need. So volume of A can transition into moles of A, which can transition into moles of B, which can transition into volume of B. So looking at a problem for this. All right. There's that sort of generic flow chart that we just wrote out. All right, the relationship between volume of A and volume of B. So let's look at this problem right here. It says we've got a equation H2SO4 plus 2NaOH produces Na2SO4 and 2H2O. Pull up that whiteboard and transition some of this over. Yeah. All right. So for our given problem, it's H2SO4 plus 2NaOH to produce Na2SO4 plus 2H2O. Oh, come on. Not gonna let me paste it, are you? All right, well, I'll just write it out. So how much 0.125 molar NaOH solution do we need to completely so this problem here, how much of a 0.125 molar NaOH solution do we need to completely neutralize a 0.225 liter of a 0.175 molar H2SO4? Icky, but we're going to try and break it down here. So first off, I know I'm going to be needing to do something with solution stoichiometry because there is a balanced equation that was given to us. They don't just give that to you for fun. There's a reason for it. Another thing is, do you see how some of the information is talking about one compound, NaOH, and the other information is talking about this second compound, H2SO4? Those are two different materials. That means we need to transition from one compound to another, and the only way to do that is through stoichiometry. So what I like to do is first determine, because we've got this whole flow chart of volume A and volume B. So let's figure out what is compound A and what is compound B. So compound A for your problems is always going to be the thing you have two pieces of information on, or you have more information on it. So in our case, I have one thing about NaOH, but I have two pieces of information about the H2SO4. So in this given problem, compound A is going to be the H2SO4. Now let's write out what that information is. So the first piece of information that I have is its molarity. I know that the molarity of this solution is 0.175 big M. Now, when I'm doing solution stoichiometry, right off the bat, I'm going to write this in a different way. I'm going to write it with that double unit because we're setting this up in dimensional analysis and the big M just doesn't work as well. So instead of saying that this is 0.175 big M, which it is, I'm going to say it's 0.175 moles, specifically moles of the H2SO4 in every 1 liter of the H2SO4 solution. I remember we did that earlier. We just took the number and stuck it up on the top with the mole. It's a mole per liter. So right off the bat, when you're doing solution stoichiometry, get your molarity into moles per liter. What's the other thing that we know about compound A? We know its volume. Okay, so the volume over here, it says, hey, volume is equal to 0.225 liters. Always make sure your volume is in liters. So if they give it to you in milliliters or cubic inches or whatever, you probably won't get it in cubic inches, but you may see it given to you in liters, rather milliliters, convert to liters, just right off the bat, get it into the unit we like. So for solution stoichiometry, we like to see mole per liter and we like to see liter here. So compound B is going to be the other thing. The thing you have less information on and the thing you're trying to work towards. So we're trying to work towards compound B is going to be NaOH. So I know, what do I know about NaOH? I know its concentration. I know the molarity is 0.125 big M. Again, I'm going to right away change that into a mole per liter conversion factor. So it's the same thing as saying that I have 0.125 moles, and I'm going to give it moles of NaOH. I want to put what the compound is, just so I don't confuse myself, for every 1 liter of NaOH, because we've got two concentrations going on, right? We've got a concentration up here and a concentration down here. So let's customize them. And then the final thing is I'm looking for the volume. When it says how much in a solution problem, it's talking about the volume, okay? Unless it explicitly says, give it to me in grams, search for the volume. So we want to find this thing. The next thing I'm going to do is just sort of make a flow chart that's customized for our specific problem. So volume A is going to be H2SO4. So I want to go from volume of H2SO4 into moles of H2SO4. Now from moles of A, I can go into moles of B, which is NaOH. So I'm going to then go into moles of NaOH. And then finally, I can go into volume of NaOH. Remember that H2SO4 is acting as our A compound, NaOH is acting as our B compound. And I'm really trying to, like, I don't want to say dumb it down, but really simplify each step here, or really, expand each step here so you can see exactly what is happening. Now, the intermittent steps, if you don't remember, let's just go ahead and fill them in. So how do we get from here to here? Remember, this is molarity. Okay, specifically, we're going to use the molarity of H2SO4. The middle step, going from moles of one thing into moles of another, we do that by using the coefficients from the balanced equation. And then the final step here is where we use molarity of compound B, which is the NaOH. So I'll walk you through the first dimensional analysis for this, and then I'm going to give you guys a problem to do on your own. So first we start with, and I know this feels like we haven't even started the problem, we've done like a lot of setup, but this kind of dummy proofs the last part of it. So let's do what the flowchart tells us. It says, hey, start with volume of H2SO4. So there's my volume of H2SO4 right there. 0.225 liters of H2SO4. There's no debating it. It's in there in that spot. What I need to do to get from volume into moles is use the molarity of H2SO4. Where is my molarity of H2SO4? It's right here. I want to use it just as it's written here. Because liter is on the top, I want liter to be on the bottom. So 1 liter of H2SO4 is equivalent to 0.175 moles of the H2SO4. What that allows us to do when we take our volume and we multiply it by the molarity, pretty much, is it allows the liters to cancel out. Now I have just moles of my starting compound, H2SO4. Great. The next step is to go from moles of my initial compound into moles of the desired compound. That's the solution stoichiometry part. Or the stoichiometry part. So we want to go from H2SO4 here on our balanced equation to the NaOH. And the coefficients tell me it's a 1:2 ratio. So the next step is to put that ratio, the H2SO4 goes on the bottom. The mole of NaOH goes up on the top. Specifically, let me make this mole. And the ratio is 1 H2SO4 is 2 moles of NaOH. The last step is to go from moles of NaOH into volume of NaOH. Now, how do I do that? Well, I'm going to use my molarity of NaOH. Okay, this thing right here. But instead of using it in this setup, I'm going to actually reverse or flip-flop it. If I put the liter on top, the 1 liter of NaOH on top per every 0.125 mole of NaOH on the bottom, what that's going to allow me to do when I plug it into the dimensional analysis is cancel the mole value out and end up with a liter value. So 1 liter of NaOH is going to go up on the top. That's going to be for every 0.125 moles of NaOH on the bottom. So what we do is we take our initial volume, we multiply it by the molarity, we use the coefficients, and then we divide by the second molarity. It doesn't always work out that way. If we're trying to find the final molarity instead of volume, we have to do something different. But if you're given the volume and you're trying to find the volume, it'll follow that pattern. And what we'll see is liters of the initial thing cancel out, moles of the initial thing cancel out, and moles of the final thing cancel out. The only unit we have left is the unit of liter. And so we can plug in chug 0.225 times 0.175 times the 2, and then divided by the only thing that has a value on the bottom is that 0.125. Okay, and we get 0.63 liters of the NaOH solution. So they're kind of messy problems. And real easily, people sometimes will see an initial volume, or they'll see a volume and a concentration and another concentration, and they think it's solution dilution. If there's a balanced equation, you definitely need to use, you definitely need to do solution stoichiometry. Any questions on that outside of the fact that we obviously want to do some practice on it? Any steps in here that you're like, I'm not getting where that came from? Okay, so I'm going to give you guys a problem, and what I want you to do is set up this part and this part. You don't have to actually solve it yet. I just want you to get the information organized and do like a customized flow chart for it. So I'm gonna write a problem somewhere where we can still see some of this work. Put it up here. How many milliliters of HCl are needed to neutralize 55.8 milliliters? Let me add a little, I need to add a little more information here. How many milliliters of 4.77 molar HCl are needed to neutralize 55.8 milliliters of a 4.63 molar NaOH solution? How many milliliters of a 4.77 molar HCl solution are needed to neutralize 55.8 milliliters of a 4.63 molar NaOH solution? And the balanced equation for this is pretty easy balanced equation. Hydrochloric acid plus sodium hydroxide produces water, H2O, and the salt, NaCl. And all of these are in fact a 1-to-1 ratio. Okay, so first step I want you to do for this problem is repeat figuring out what compound A is, what compound B is, file your information into the correct spots, and then give me a customized flow chart. I'll give you about 3 minutes to organize the information. We'll come together, look at that, and then I'll give you another chance to do the actual calculation. Okay, I'm gonna make some space here. Get rid of this. Leave that last little bit down there. Okay, so right now, initially, all I want you to do really is just organize your information. So we're trying to figure out what our compound A is and what our compound B is. Compound A is going to be the thing we have two pieces of information on. So in this case, the NaOH is acting as our compound A. Compound B is whatever we're going to be trying to work towards. In this case, it's going to be the hydrochloric acid, the HCl. All right, we have two pieces of information on compound A. We know its molarity. So the molarity of this thing is 4.63 big M. And I'm going to, again, right off the bat, just turn that into moles per liter. So 4.63 moles of NaOH and every 1 liter of the solution. The second thing I know about the sodium hydroxide is its volume. The volume is 55.8 milliliters. Milliliter is not going to work in this problem because we're using molarities, which are in units of moles per liter. So I'm just going to, again, convert this right away into liters so I don't get confused. Move the decimal over 1, 2, 3 spots. So it should be 0.0558 liters, specifically of NaOH. The stuff I know about compound B. Okay, I know its molarity. Molarity for this thing is 4.77 big M HCl. And I'm going to just get that right away into moles per liter. So 4.77 moles of HCl in every 1 liter of the HCl solution. Volume is, well, that's what I'm trying to find. Okay, so the kind of customized flow chart for this problem is to go from volume of A, which is NaOH, into moles of A, which is moles of NaOH, into moles of B, which is HCl, moles of HCl, into volume of HCl. Follows the same pattern as the problem before it, just slightly different numbers and a different balanced equation. So in order to go from volumes of NaOH into moles of NaOH, I have to use the molarity of NaOH. Molarity of NaOH, or molarity, not moles equals, but molarity, so this thing here. The ratio for this problem, HCl to NaOH, is a 1-to-1, right? I know 1 mole of NaOH is equivalent to 1 mole of HCl. It's not always 1-to-1, right? The last problem we did was a 1-to-2. So do make sure you take into account the coefficients. And then this final step here, we're going to use the molarity of HCl, which is this thing down here. All right. So I'm going to give you all another 3 minutes to actually take your information and plug it into your dimensional analysis following this flow chart. I have left this one up here so that you can sort of mirror what we did, since it's a pretty similar problem. And I will see you all in 3 minutes or so. All right. Give yourself another 30 seconds or so. I'm gonna raise this up. So if, as you get better at doing these, you may not have to lay it out so detailed, but I do think in the beginning, this can be helpful just to file where all the information goes. So my flow chart says to start with volume of NaOH. That's this number right here. I've already got it converted. So 0.0558 liters of NaOH. Now, I want to get from volume of NaOH into moles of NaOH. So the way that I'm going to do that is multiply it by my molarity, not written with big M, but written as a double unit. So we'll put the liter on the bottom. 1 liter of NaOH is equivalent to this 4.63 moles of the NaOH. That allows the liters to fall out. And now we're just in the unit of sodium hydroxide, NaOH. From there, to go from moles of NaOH into moles of HCl, I use the coefficients, one of these for every one of these. So that's actually, it's just a 1-to-1, but we're still going to write it in because it's not always a 1-to-1. So 1 mole of 1 mole of NaOH for every 1 mole of hydrochloric acid, HCl. And then the last step is to go from moles of hydrochloric acid into the volume of hydrochloric acid using what we have written here, molarity. So here's my molarity of hydrochloric acid, but I don't want to write it like this. I want to flip-flop these because I want to come up with a unit of liter. I want liter HCl, and we need to, sorry, my daughter is screaming very loud for me. 4.77 moles of HCl. So we'll flip-flop this. Now, what that allows is the hydrochloric acid mole value to fall out. So 4.77 moles of the HCl is equivalent to 1 liter of the HCl. And look at how nifty that is. There go the moles of the NaOH, and there goes the moles of HCl. Hold on one second. Sorry, we ran out of milk. My husband is like running to the store right now as I'm trying to juggle all of it. So this is going to plug our information out in liters, 0.0558 times the 4.3 divided by the 4. And we're going to get a value of 0.054. Let's see, it looks like I gave you guys. I'll give you 3 sig figs. Okay, 0.0542 liters. Now the problem, real fine tune here. It says give it to milliliters. So we do want to convert this to milliliters. 1, 2, 3, 54.2 milliliters. Okay, the problem will not spit it out in liters. It's going to spit it out in milliliters. Or I'm sorry, it'll spit it out in liters. You have to convert to milliliters. So that's how you do solution stoichiometry. It's kind of messy. We are going to do a little bit more of it when we get into the acids base chapter. So I'm not going to do another example of it tonight, also because my child is having a meltdown. But we will revisit this. So we will do one more next week. Next week will be acids and bases. And then you guys are like done. You've got your test and your final, and then you're done. And then you pass and you move on. So make sure, if you haven't yet, to register for classes so that you can get the classes that you want to take. Because if they don't start to fill up, they will cut classes and you'll just have less options. So get registered as soon as you can. If you have any questions, feel free to stay around. Otherwise, I will see you guys a week from today. Thank you for your patience. Bye. Have a good night too, Cynthia.